Welcome to this MPAI presentation on the call for technologies, connected autonomous vehicle architecture. So they are, the idea of making self-driving it's a long life. And today we have a level-based classification of cars that have self-driving capabilities by the SAE. Many believe that self-driving cars will have a positive impact on the industry because of the huge new manufacturing industry that will be generated, society because of some optimizations, and in general on the environment. MPAI proposes a standard-based approach to accelerate the introduction of a mass market of connected autonomous vehicles. So first of all, let me say a few words about MPAI. So first of all, MPAI is moving picture, audio, and data coding by artificial intelligence. It is an international, unaffiliated, not-for-profit standards developing organization. We are based in Geneva. We develop AI-based data coding standards, and not just the standard, but we also add a clear intellectual property rights licensing framework. This is very important for facilitating and accelerating the use of standard technologies. So why is MPAI engaged in connected autonomous vehicles? Because, well, for several reasons. CAVs must be based on a lot of AI to process different data with high quality, with stringent requirements, and processing data with artificial intelligence is MPAI business. Connected autonomous vehicles components must operate in a secure environment, and we do have an environment. It's called the AI framework that we are extending it to provide the environment with security, stringent security. Then there is a strong connection between connected autonomous vehicles and the metaverse, something that I will say about during this presentation. And indeed, we are developing a metaverse architecture standard. What are we doing in terms of standards? Our approach is that we don't standardize big systems, but we standardize the components of big systems, which means that if there is an AI application, we divide it into smaller components, we call them AI modules. We aggregate them in one or more AI workflows, and we execute the workflow in a standard environment, this AI framework I was talking about. That's why we have one standard, which is the foundational standard, AI framework, and a second one, which is also very important, which is called the governance of the MPAI ecosystem. Every standard generates an ecosystem. There are other standards that we have published. So this is the 4 technical specifications that we currently have: context-based audio enhancement, compression and understanding of financial data, multimodal conversation, and neural network watermarking. These, of course, are in addition to the 2 that I have mentioned in the preceding slides. Then we have 2 technical reports that concentrated on metaverse, which is a big project that we have, and it is connected with connected autonomous vehicles. There are far more standards that we plan to publish soon. 2 are extensions of existing standard, the AI framework version 2 standard that we are involved with security, and a multimodal conversation. And then we have 3 new standards on avatar representation animation, connected autonomous vehicles with what I was talking about today, and the MPAI metaverse model architecture. But that's not yet, because we have more standards to our artificial intelligence for health, and the second one, which extended reality venues. And then we have 3 more standards that I mean we are studying, and we hope that will be soon become the 2 call for technologies. That is what the 2 first artificial intelligence for health and extended reality venues will be very shortly. What's the relationship with IEEE? Well, simply, IEEE has adopted as our standards, as their standards, 5 OR specification, the AI framework, the audio, multimodal conversation, finance, and neural network watermarking. And all this has been achieved in less than 3 years with the help of many dedicated people, and they are the those who make this possible. So let's talk now about the subject of this presentation, which is connected autonomous vehicles as seen by MPAI. First, we have a question. Do we have a definition? Well, something like system that understands the mission from what the human says, like take me home or stop here, park there. I've changed my mind. I mean, all this kind of things should be understood. Then, based on what the human says, it plans a route, as I say, from here to home, for instance. Then it senses the environment and represents it in an appropriate way. This representation must be standard, because then it is possible to exchange representation, maybe in a scalable form, with other CAVs or entities that are CAV capabilities. Then it decides how to execute the steps of the route. And finally, it implemented the decisions about reaching a point through commands to the motion actuation subsystem. So let's go back to the issue of connected autonomous vehicles and standards. So I'm repeating what I said. Today, CAVs are a niche market. Well, if it is a market, it is not really even that. But standards can convert niche markets into mass markets. And to show you what I mean, is that we just have to look at the MPAI story. I mean, of course, digital television would have happened, but the MPAI standard facilitated in an enormous way, because the critical components, they're very sophisticated, very expensive to design, could be done safely with the assurance that there would be a global market. Components is for connected autonomous vehicles is what we are aiming at. So we think that AI provides excellent solution for connected autonomous vehicles, and also that the operation of a CAV should be explainable. And standards do exactly this. They promote the quality of the product, reduces the price, explain the operation, assuage consumer concerns, and provide the tools for regulation. So we have two approaches to transform a market, a niche market, into a mass market. The first is that, okay, we have the SAE levels. Let's wait for the market to produce cars that have higher and higher SAE levels. The other one is that the market produces CAV that are based on a standard architecture. Why should they do that? Because this architecture enables component manufacturers to produce components and then put them on the market, because there is a global market of components with standard interfaces. And the car manufacturers, okay, they access a an open global market of components, and these components have standard functions and interfaces. And importantly, a standard should have the means to test for conformance. And this is what MPAI intends to do as soon as we have the technology standards in place. So then what is an MPAI call for technologies? It's because we have a very rigorous process to develop standards. It is 8 steps. Here you have the first 4, which is someone comes with a proposal, then we identify the use cases that would be supported by this proposal or standard. Then we develop the functional requirements and also the commercial requirement. The commercial requirements is more in quotes, but it's still the idea of having not just the functional requirement, but the commercial requirement as well. The call for technologies, which is the 5th step, requests anybody having technologies in line with the functional and commercial requirements and are ready to license their technology according to the commercial requirement to make them available to MPAI for drafting the standard. So this is where we are. And what will be next? Okay, then when we have the technology, we develop the standard. So this is the reference model of which is the first element of the standard. So here we have a guy who wants to go home. Here is their car. Then the human says, I want to go home. This is understood by the first subsystem, HCI, which forwards the request, of course, in another language, because the subsystem don't speak the same language as humans. And then the autonomous motion subsystem produces possibly 2 or 3 options that are communicated back, and there is a dialogue. Eventually, the autonomous motion subsystem develops, implements the route that has been selected. So the environment sensing subsystem tells the autonomous motion subsystem where the car is, because the autonomous motion subsystem is pure brain. It doesn't have any sensor, but the environment sensing subsystem is the hands and the eyes and the ears and the nose and the taste of a car. So this information, I mean, the emotion actuation subsystem, which is the mechanical part of the CAV, forwards environment information, can be velocity, speed, and acceleration, position, and the other environment data, so that the environment sensing system can put together all this information and create what we call basic environment information. Why is it basic? Well, because that is the best that the car could do with its own forces. But there are more people around. So as much as we call for help for other people, what do you think about this? So it may ask another car, can you give me what you see from your viewpoint? Because from my viewpoint, this is not so clear. So we have, again, a dialogue in another sophisticated and different language, the result of which is what we call the full environment representation, which is the best understanding of the world that is possible with the forces of the CAV and the help of other cars and systems around. So based on that, it's possible to make giving instructions to the motion actuation subsystem. Now, please go for in 5 minutes. I want to go to that place, and when I am at that place, you are at that place. Then I want you to have that position, that orientation, that velocity, and that acceleration. And of course, the motion actuation subsystem tries its best to implement, but not necessarily it is able to do it. And in that case, it will feed the information back to the autonomous motion subsystem. To conclude this slide, I would like to add this communication that is potentially happening between the human-CAV interaction of one CAV with their peers in other CAVs or other devices. And the call for technologies request comments on business system partitioning. Of course, this is very high level, but you will see more in the next slides. The level of detail that we provide in this partition. We have a disclaimer. We are interested in bits and artificial intelligence. We are not interested in mechanics. It doesn't mean that mechanics is not important. Absolutely not. Simply that that is not our intention. We intend to develop the interfaces of the motion actuation subsystem with the mechanical part that implements the instructions. So here you have a few terms and definitions. We have more than 100 terms and definitions. So we have HCI, the human-CAV interaction, the environment sensing subsystem, the autonomous motion subsystem, and the motion actuation subsystem. These are the 4 subsystems. Then we have the environment sensing technology, which is any technology. We'll see in a minute the others. And then we have the basic environment representation and the full environment representation that I already talked a lot about that. Just a very quick look at the environment where subsystems are implemented. So a subsystem eventually is a workflow. It's a workflow of AI modules. And we have said that we want to give precise interfaces between AI modules. So it is acute there. So far, the specification assumed that the environment was secure, but it did not say how security was implemented. Now we are defining an API whereby an implementer can get security support through what is called the security abstraction layer that you see here. Okay, so here I'm starting to present the 4 subsystems. There's so much of information that it would take many hours, but that is not the purpose of this presentation. The purpose is to make you aware that there is so much more that should be studied, considered, and everybody is invited to comment back to MPAI about how certain issues should be addressed. So let's take the first subsystem, human-CAV interaction. So we have 5 slides for each of the subsystems. The first one is about what is the function. It authenticates humans. It converses based not just in terms of words, but also understanding what is the internal status, the emotional status, state of a human. It converses with the autonomous motion subsystem, like I have said. Passengers can navigate the full environment representation. Of course, the full environment representation has been developed for a consumption by a non-human brain, but human too can have access to it. Then we don't want the CAV or the human-CAV interaction to appear as an abstract entity. We want to give a body and a face. That's why we wanted the HCI to appear as a speaking avatar that shows the personal status. And the personal status depends on the content of the conversation, the information that the CAV knows, the personal status of the human. And okay, there are a lot of areas on which comments would be welcome. So this is the reference architecture. It would take a long time to explain, but you see that here we have the blue means the subsystems. The green means the AI modules that we have inside its subsystem. So here, for instance, we have an audio scene description. So because, you know, you cannot expect to be in a laboratory situation where the car perceives exactly my voice without any noise at all. It's not like that. There can be other voices, noises, and so on. So we needed to create a map of all this so that the CAV understand which is the speech that it should focus its attention on. Same for visual scene description, because it is good to understand who is exactly the person, and not just outside. This is also inside when humans are in the cabin, because even in that case, there could be 3 people, and the CAV, the human-CAV interaction, may be asked to join a conversation or to answer questions that people can ask, and therefore it's important to have a precise location of all human. So this one is of course very interesting in the sense that it is the remote human-CAV interactions that exist in other cars as well. So let's take the second part. This is the input and output data of the human-car interaction. Just a second back here. So we are talking about these data here and these data here. Okay, so this is what we are saying. And so we are just naming the data, and we are commenting the data. The fourth is that, okay, we have AI modules. Can you tell me what these AI modules do? Okay, let me take, for instance, the full environment representation viewer. So this is something that the passenger uses in order to see what the car sees. So this converts the full environment representation produced by the environment motion subsystem into an audio-visual scene descriptors that the human can perceive because it is rendered, possibly on a head-mounted display, and so on and so on. I don't want to spend more time discussing that. Finally, we have which are the input-output data of each AI module. So this is what you see here. So in the case of audio scene description, we have generally audio signal, and the result is a series of speech objects. Same for video, same for speech recognition, physical object identification. What is this? So yeah, I may need to ask my car, hey, I would like to have something like this. Can you take me there? And so this, if you say this, is very clear to us, but it is not for the CAV, and therefore we have an AI module that does that. Next, the environment sensor subsystem. So we have functions. It acquires environment information. It uses radar, LiDAR, cameras, ultrasound, offline maps, audio, GPS, and possibly more. Then it receives the spatial attitude that is computed by the mechanical part of the car, and then it produces a series of basic environment representation that are passed to the autonomous motion subsystem. So here you will see the partitioning of this second environment sensor subsystem. So this is where the spatial attitude generation is perfected by using the spatial attitude that comes from the motion activation subsystem. And here you have a series of AI modules that are in charge of developing the scene description for radar, LiDAR, for cameras, ultrasound, maps, and audio as well. We also have one that is about recognizing traffic signals, because of course, recognize the traffic signal as an important function. So all this is fused in the environment sensing subsystem data fusion and passed to the autonomous motion subsystem, as we said. So here we have the input-output data of this subsystem. Here we have the functions of the AIMs. So we have, for instance, ultrasound scene description produces the scene descriptors computed from ultrasound data, and so on and so on. Then finally, we have the input-output data of the environment sensing subsystem AIMs, and of course, the data fusion is the most important one because it receives a lot of data here, those that we have seen in the figure, and what it generates is basic environment representation, but not just that, because there may be something that even the environment sensing subsystem that is not particularly smart, but can understand that it's something that should be considered by the autonomous motion subsystem with a high priority. Let me go to the autonomous motion subsystem. It computes the route, it receives the basic environment subsystem, it communicates with other autonomous motion subsystem in other cars, it produces the full environment representation, it sends commands to the motion actuation subsystem and receives information back from the autonomous motion subsystem, because the example that is very easy to consider, the autonomous motion subsystem may say, I want to be at the speed of 100 kilometers per hour in the next 5 minutes, but the motion actuation subsystem may detect that there is ice on the road, and therefore this is not possible, and therefore this triggers back reconsideration of and the reconsideration is here because here you will see what produces the basic environment representation. This is the dialogue with the human and the HSCI. So this is a series of AIMs. Well, okay. We start from the root. So this is set. Then after this, I decide, okay, so let's break the route, because the route may be very hundreds of kilometers. So there are paths, and in a path, okay, how do I plan the individual motions? Then I am now probably ready to tell the motion actuation subsystem to execute, but we have a final check, which is the obstacle avoider that may say, hey, wait a minute, this cannot be implemented because we are too, because the situation has changed, because suddenly there is a new object that has appeared, and you should reconsider the instruction that you wanted to give to the command issuer. So here again we have the input-output data. Here we have the functions. So this is much more elaborated because we have identified that, for instance, then several steps that an obstacle avoider should perform. Then we have the input-output data of the individual AIMs. And finally, we have the fourth subsystem, the motion actuation subsystem. So this is, it transmits spatial and environment information from a mechanical subsystem, but also from sensors, for instance, humidity, temperature. And it sends it to the environment sensing subsystem, which is the one that builds the first environment representation. Then it receives commands from the autonomous motion subsystem, but the autonomous motion subsystem has a subsystem itself, as we can see here, in the sense that it has a wheel motor, it has wheel direction, and it has brakes. So if I say I want to be in 5 seconds, I want to be at that position with that orientation, this must be translated maybe into an action on brakes or an action on motors because I needed to accelerate, or I needed to change the direction of the wheel because in order to be there, I needed to change the direction. So this is what happens here. The input-output data are say here. So you have odometer, speedometer, accelerometer, environment data. Then we have the commands coming from the autonomous motion subsystem, brakes, wheel direction, wheel motors. So these are the inputs. And the outputs is, information about position, velocity, acceleration. Then it receives environment data and produces environment data and provides a response to the motion actuation subsystem about how the command has been executed or is being executed. Then we have the functions. It's rather simple, and I have already explained. And finally, we have the data. Again, I have already explained, I believe. So this is the presentation of the body of the connected autonomous vehicle architecture technical specification that we wanted to develop, and we are requesting comments on it. But we have, in addition to the AI framework, which is an important MPAI component for our plan for CAV standard, we have a second one, which concerns the metaverse. So what is a metaverse? So we have a kind of definition, which is a word that should never be used in association with metaverse, because there are so many definitions that we don't want it to be the ones producing the n+1. So it senses data from the universe, it processes the data, it produces environment, virtual environment that are populated by objects. Then it processes the objects that are in a metaverse instance, or potentially from other metaverse instances as well, and eventually it affects the universe or the metaverse in ways that are consistent with the goal set for the metaverse instance. So, of course, a metaverse instance created by a CAV is very different from the metaverse instance that is created for people to play games, of course. But, you know, the technologies and the philosophy that is underpinning the notion of a metaverse are very similar. So consistent with the goals, effective within the capabilities, and comply with the rules set for the metaverse system. In the case of a CAV, it is about complying with the rules, with the laws. In case of games, we have other rules, but you know, when you translate that into digital language, things become very similar. So how is our solution for a metaverse specification? We say that a metaverse is a set of processes. What do these processes do? They perform actions on data, but they can only do if they hold the right to do that. Then they may request other processes to perform actions by transmitting a request. So if I am asking another CAV, can you give me what you see in this direction? Well, first of all, I must make sure that the guy I'm sending this request is really the guy that it claims to be, and vice versa. Then it responds to a request action and provides the information. As I said, the information that says, in this direction, I see this particular object. And then it can also communicate with the process in another instance through a resolution service, which is what this is what I was meaning by authentication and so on. So here we have a very, very simple example, which is one use case that we have in the many use cases that we have developed for the metaverse standard. So here we have a human. The human is telling the ACI, I want to go home. and the ACI translates the request into the AMS language. The AMS does the job and provides a response, and the ACI communicates the response to the human, and there could be a recycling of question and answers. And this is represented by this workflow that I will not present for sake of saving time. But we have a second case. So here we have again the same human. Now the human is, say, sitting in the car, and what happens? Here we have an autonomous motion subsystem of a car A, and now it requests the autonomous motion subsystem of a car B information about, as I said, what do you see in that direction? And here is the information coming back. Now we have the human, and the human would like to see the landscape that is seen from another car. So the request is given to the HCI of car A, which forwards the request to car B. The car B sends the information back so that the user can see. So this is a very, very simple example that says how intimate can be the relationship between connected autonomous vehicle and metaverse, and the MPAI is working on both. This is the end of the technical part of the presentation. A few words of what I was saying before about framework licenses. So for each standard that we develop, we have a framework license. This is a very short presentation about the framework license for connected autonomous vehicle. First of all, what it covers? Oh, it applies for the standard, CAV standard, as it will be defined. It is not defined yet, of course. That is in the plural, and the number is not assigned because we don't have it. All contributors to the standard shall confirm in writing their intention to make available a license for their essential IP based on condition of use of the license that will come next. So we have a set of definition that I will I will skip. Few words about the condition of the use of the license. I repeat, this is not a license. It expresses general principle that will be followed when the final license will be drafted. So the license will be in compliance with competition law. The license will grant access to essential IP in a non-discriminatory fashion. The license will cover all claims to essential IP and copyright of a licensor that are practiced by a licensee. So if you wanted to implement the standard, I mean, the IP holder guarantees that they will grant a license for all their essential IP. Then the license will cover the development rights, but also the implementation rights. Then we have a general statement about the license being subject, potentially being subject to legal, bias, ethical, and moral limitations. Don't forget that we have AI that is involved, and so we wanted to be cautious about this. Royalties will apply to a baseline profile and potentially to other profiles that contain other technologies. Applies to any implementation, but we are excluding something, and I will talk about that in a second. And the royalty will apply on a worldwide basis. Then an implementation may use other IP, extending the specification, for instance, to provide other functionalities. So what are the exemptions? So these are essentially because we may very well license free of charge implementations for the purpose of evaluation or to create demos or technical trials. The license may be granted free of charge for particular usage if licensor so decides. So this is the general terms. And a license free of charge, but it must be for a limited time, limited amount of forfeited royalties, will be granted on request. And number 8 is also very important in the sense that as part of the standard development, the patent, the IPR holders will select a patent pool administrator. Finally, the license will be used before implementation are available on the market. Then the total cost of the license will be in line with the total cost of the license for similar technologies. And the total cost of the license will take into account the value on the market of the standard essential IPR. You may think that this is limited importance, but actually the principle that you see here have a far-reaching implication, and we are very proud that the principal members of MPAI have agreed to this framework license. Next steps. So we are now at the presentation. If you intended to respond, please make a pre-registration by the 31st of July. This is recommended, but it's not mandatory. And if you pre-register and you don't submit anything, that doesn't matter. I mean, we want to give the maximum freedom. Respondents should submit responses by the 15th of August. Then we intended to publish for community comments the specification on the 23rd of August. And we intended to approve and publish the standard on the 29th of September. So the conclusions. So we are requesting technologies to develop a technical specification that partitions connected autonomous vehicle into subsystems, the 4 subsystems. Each subsystem is partitioned into components. We specify the function, the interfaces, and the topology of AI modules of the subsystems. And we specify the function and interfaces of the components. The specification will benefit from 2 other technologies, 2 other standards. The fact that the AI workflows can be executed securely in an environment, and the metaverse model that I have presented before. Then, if you think that this is the end of our work, the answer is no, it's just the beginning. And the next step is that we want to develop the functional requirements of the data exchange. For the moment, we are simply giving a name in the summary description, but we would like to develop precise functional requirements, and there are very serious advantages in doing that. I don't have the time to explain that, but this is what will guide our next work. With this, I would like to thank you for participating in this presentation, and I look forward to working with you on this exciting MPAI project. And that's the end of the presentation. Thank you for your attention.